Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Motion of Particles Through Fluids Part 3. We have been discussing several aspects about the settling of particles through fluids, both spherical and non-spherical particles. Non-spherical particles, generalized expressions for the terminal velocities etc. that we have derived and then left as it is, both in gravity and centrifugal field. But under the case of spherical particles, we further simplified those equations for different flow regimes, Stokes flow regimes and Newton's flow regime, and then we developed their settling velocity equations. So those things we have done for a single particle like settling in a kind of infinitely unbounded fluid. So that is, the particle is settling without any kind of hindrance or without any kind of disturbance from the neighboring particles. That is, in the neighborhood of the settling particle there is nothing other than the fluid medium, and then container wall in which the liquid is taken, in which the particle is settling, that container wall is also far away from the particle. So there is no influence of the container wall on the particle settling velocity, because if the particle is settling in a narrow container, so the particle velocity would also be affected by the wall effects. Because of the presence of the wall close to the particle, the velocity gradients near the particle would be disturbed, and accordingly the particle settling velocity will change. So whatever the things that we have discussed till now, last 3 lectures about the particle settling in a fluid, that is only for single particle settling in an unbounded infinite amount of fluid. The fluid is also a kind of Newtonian fluid. That is that part only we have seen. But in general, in reality, what happens, we do not have a kind of a single particle system only. We have real life situations. Large number of particles are settling, or large number of particles are flowing in a kind of fluid stream, or there may be a relative velocity between fluid stream and then this large number of particles. Right, under those conditions, what is the settling velocity of those number of particles, large number of particles, or on what basis how those particles are being separated into the different fractions etc. So those things we cannot get the information from the single particle equations whatever we have developed. So that for that case, that we are now trying to do hindered settling. We are going to discuss in this particular lecture about the hindered settling, where the large number of particles are there, right. So large number of particles are settling, okay, in a kind of fluid like this, right. And then for the time being, we assume that particles are of same shape and size, so that developing the equation would be easier for us. Let us say now this in the particle, this is in a kind of a fluid medium. We have taken a particle. Let us say this is the target particle. We are trying to settle it down, right. So this is our target particle, right. So now when it is settling here, so whatever the particles nearby are there, they are affecting its settling velocity, because this nearby particle, presence of nearby particles, what happens, the velocity gradients around these particles are at the surface of the particle, velocity gradients are strongly influenced by these particles, neighboring particles. That is the reason the settling velocity of this target particle in a kind of suspension is going to be very much different from the same particle settling alone in a kind of free stream conditions or free settling conditions. So how much difference it is, that is what we are going to see here in this lecture, right. And then further, what happens, let us say this particle has moved here. So already there is a particle here. So when it is coming, so the downcoming particle may be pushing here, right. If assume there is a kind of there is no particle here in this region. So when this particle is settling coming here, right, now I am just putting as a kind of dotted line so that to have a clarity. So when this particle comes down and to this level, whatever the fluid is here, that is being replaced by the particle. So that fluid what will do, that will try to move up, right. So because of the buoyancy, so that fluid raise velocity of the fluid that may be affecting the settling velocity of the neighboring particles, because in the suspension not the one single particle settling, a large number of particles settling. So the whatever the upward motion of the fluid is there because of the downward motion of this particle. So this particle, let us say this target particle, first particle 1, when it is settling here, so the fluid underneath here, that is being replaced. That fluid, what will try to do, that will try to move up because of the density differences. When it is moving up, so there is a kind of upward motion of this particular liquid. So that upward motion of the liquid is going to affect the settling velocity of the neighboring particles, because neighboring particles are also settling. All these particles are settling at different settling velocities if they are different in size and shape, right. So that is what it is going to happen. Now obviously these circumstances, whatever the settling velocity of the particles is there, that is not going to be same as the settling velocity of the single particle in the same fluid. So now what we understand, large number of particles are present as in suspensions in general. Okay, in real life applications it is not possible that to have a single particles as we have studied. So surrounding particles interfere with the motion of individual particles, as I explained. That is, the velocity gradients surrounding each particles are affected by the close presence of other particles. So that effect also we should take into the consideration. Settling particles displace the liquid and an appreciable upward velocity of the liquid is generated. So that upward velocity of the liquid may be hindering the settling of other neighboring particles falling down. Okay, settling. So therefore velocity of the liquid is appreciably greater with respect to the particle than with respect to the apparatus itself. Let us say if you take the relative velocity between the liquid and then container wall. So obviously container wall at the kind of zero velocity because they are fixed kind of thing. Now if you take the relative velocity between the upward liquid motion and then container wall, and you take the relative velocity between the upward motion of the liquid and particle, then obviously the whatever the relative velocity between upward velocity of the liquid and then particle is, that will be much higher than the other case. Okay. So for hindered flow, settling velocity of particles is less than that of free settling velocity, because when one single particle is settling, there is no disturbance of the particle in their trajectory path. Let us say the particle is initially here, that is coming down here, so it can smoothly fall down without any hindrance. But in the case of hindered settling, if there is a particle when it is coming down here, so there are particles nearby, so they may be objecting its flow. So additional resistance is there because of the neighboring particles, because of the hindrance of the neighboring particles. So the settling velocity of suspensions in general is going to be much smaller compared to the free settling velocity of single particle of the same size and same density in the same fluid. Okay. So because of this one additional resistance, the drag expected or the drag experienced by these particles, large number of particles in suspension, is going to be much higher compared to the drag on a single particle under the free settling conditions. Obviously now here in the case of suspension, the resistance is more, so obviously the drag would be more. So they would be expecting or experiencing more drag. True drag force is greater in the suspension, and then viscosity of suspension or mixture is also going to be different compared to the viscosity of a pure liquid here. So because now this suspension, in the suspension these particles are very small. Sometimes what happens, when these suspensions are not settling at a kind of appreciable velocity, or they may be taking large time to settle, indeed in general they do. So then what happens, the liquid becomes a kind of some other complex liquid. Okay, complex fluid, it will take a form of another complex fluid which is having a fine particles as a kind of suspension in that one. So let us say initially you have taken water and then you added a kind of some amount of particles, very fine particles, and then it has become a kind of suspension, let us assume, right. So then that suspension is stable, it is not settling for a long time. So the fluid properties of that liquid, initially it is liquid, so it was initially having the density and viscosity of water, at that temperature and pressure conditions. But now after adding these particles, it has become a kind of suspension. So, and then these particles are not settling, they are taking long time, and it's formed a kind of suspension. So then obviously the density and viscosity of that water is now no more be valid, because it's now altogether a new fluid, it has formed a new suspension in the kind of liquid form, let us say. So it is going to have a kind of different density and then viscosity. So those mixture viscosity and mixture density we have to find out. So there are several correlations or expressions are available for this mixture density and viscosity. We take a few which are famously used in general in textbooks. So viscosity of a suspension or mixture is in general given by the viscosity of the actual liquid divided by some empirical correction factor psi p. Right. So let us say water you have taken. So water viscosity divided by, there will be a kind of empirical correction factor, but this empirical correction factor, it depends on the volume fraction of the liquid. No, because initially it is purely liquid only, but after adding the particles, now it's a kind of suspension. So it is having two phases, though that phase is a kind of stable phase now, because the particles are not settling. So then whatever the volume fraction of the liquid is there, whatever the volume fraction of the solid particles are there, fine particles are there, that you can calculate. People have find this empirical correction factor is a kind of strong function of the volume fraction of the liquid that has been taken. Okay. So how it is a strong function? It is defined as psi p is equals to 1 by 10 power 1.8 to 1 minus epsilon. So here this epsilon is nothing but volume fraction of the liquid in the slurry. Okay. So this suspension sometimes are kind of useful, sometimes they are a kind of disadvantages, right. So sometimes like you have the lotions etc., or some shampoo etc. So those are a kind of some kind of suspension, some particles, some droplets kind of things are suspended in a kind of different in a kind of other liquid, and then they are forming a kind of suspension. Under such conditions you do not want them to be separated for long time, at least for a year or two, so that its expiry date is longer period. If all these particles are settling, so then the shampoo would be of no use at all. Right. So under such conditions it is going to be a kind of advantages. Sometimes you wanted to separate those particles so that you can purify them in kind of some kind of mineral ore industry etc. Right. So there is a kind of different particles are there. So along with the mud you try to wash with the some kind of liquid, let us say water, and then mud is being washed out. So but these mineral particles, if they are not settling under those washing conditions, then that is going to be disadvantages. So it depends on the application to application. So now we are taking irrespective of the applications, whatever this viscosity of suspension is there, that is defined like this. Okay. Similarly, the density of the slurry or the mixture or the suspension, now you can take as a kind of weighted average of the densities of liquid and then particle. So rho m is equals to epsilon rho plus 1 minus epsilon rho p. So rho is a kind of density of liquid, and then rho p is a kind of density of the particle, epsilon is a kind of volume fraction of the liquid phase, and then 1 minus epsilon is the volume fraction of the solid particles in the suspension. Right. So now if you rearrange this equation, or if you do rho p minus rho m, this equation, rho p is as it is, minus rho m we can write minus epsilon rho minus 1 minus epsilon rho p like this. So here this rho p and then this rho p multiplied by 1 may be cancelled out, it will be, because one is plus and rho p, another one is the minus rho p, and then remaining two terms if you take the epsilon as a common, so you have a epsilon rho p minus rho. Why are we doing this one? Because now we are trying to develop a kind of a relation between settling velocity of suspension and free settling velocity of the single particle of the same material, same density and same size, right. So that is the reason we are going to do, we are doing all this simplification. Now for Stokes law of single particle, we have this velocity ut is equals to g dp square delta rho by 18 mu. Okay. In general, the suspensions, they take long time to settle. The settling velocity is very small in general for many of the suspensions. So, usually the Reynolds number is going to be very small for suspensions, right. So, Stokes regime can be safely used, right. Okay. So, however, there may be some cases where the suspension, if they are not very stable, so then their Reynolds number may be, you know, more than REP is equals to 1, but it is not going to be very large in general, like, you know, 1000 or, you know, 10 power 4 or 10 power 4. Such large Reynolds numbers are not possible in the kind of suspensions in general. Okay. So, now here if you wanted to develop settling velocity of a suspension of the particles having size dp, okay, and then in the fluid, whatever the same fluid you have taken, right. So, then what should be the settling velocity of the entire suspension. So, for that what we do, this delta rho, that means this delta rho is nothing but rho p minus rho, right. So, this rho p minus rho, and then this mu, how should we take, how should we consider it, right. So, that is what the question here. So, for that what we do, we replace mu by mu m, that is mixture viscosity or viscosity of the suspension, and then delta rho, whatever the delta rho is there, rho p minus rho, that we replace by rho p minus rho m, because mixture density, then, you know, mixture is having a different density compared to the fluid alone rho value. So, whatever the particles they are settling now in a kind of mixture, right, or in a kind of suspension. So, that is the reason this rho, delta rho should be replaced by you know, rho p minus rho m, or rho p minus rho in general for single particle whatever is there, that should be replaced by rho p minus rho m, and then this u has to be multiplied by, and this right hand side expression should be multiplied by epsilon by epsilon, that is, you know, volume fraction of a liquid phase, or in general this you know, average velocity of the you know, in general in packed or packed bed or fluidized beds, etc., what we have done, the velocity should be divided by the epsilon, right. So, in order to bring the effect of the you know, narrow spaces available for the fluid to move on, right. So, similar way, if you do here, the velocity if you divide by epsilon, or you right hand side if you multiply it by the epsilon, so that to bring in the effect of the neighboring particles, and then simplify, then whatever the velocity you will get, that would be the suspension velocity, that would be the suspension velocity or the hindered settling velocity of those particles. Okay. So, that we are going to do now here. So, when you do this one, you will get this expression actually, right, us is equals to g dp square delta rho. Now, what we have done in this equation we rewrite here, u t is equals to g dp square rho p minus rho by 18 mu. So, here what we are going to do, g dp square we are keeping as it is, rho p minus rho we are replacing by rho p minus rho m, and then 18 mu is to be replaced by mu by psi p, right. So, that and then this u has to be divided by the epsilon, right. So, then under such conditions whatever the velocity is there, that would be the suspension velocity us is equals to g dp square, rho p minus rho m is nothing but rho p minus rho multiplied by epsilon divided by 18 mu, this psi p we can take numerator, and then whatever the epsilon in the left hand side is there, that if you take to the right hand side, that would be epsilon square. So, now what we have, this is nothing but g dp square delta rho, that is rho p minus rho by 18 mu is nothing but ut, single particle terminal velocity, this multiplied by epsilon square psi p is going to be the suspension velocity, or this is settling velocity of the same size particle in a kind of suspension. Okay, right. So, this is what we do. So, then we get here. So, now there is a relation between the suspension velocity and then terminal velocity of single particle. Why are we doing this? Because in general we have a many large number of particles, so we cannot do a kind of individual calculation for individual size particles and all that becomes very difficult. So what we try to do, we assume that the average size of the particles in the suspension is a kind of constant value. Then for that constant average size of the particle dp, we calculate the single free settling velocity, and then from there we try to multiply by the correction factor so that to get a kind of a settling velocity of a suspension. It will allow us to calculate recalculate a kind of things, how much time these particles are going to take to settle down completely or to separate in two different phases. If they are completely settling, then it will be separated in two phases, like solids at the bottom and then liquid at the top, like kind of thing. Okay. So that way you can one can analyze the quality of the product that has been prepared in like if somebody is interested in making suspension, then this US has to be very small, so that the time for settling would be very large, so that the suspension will be stable for longer period, right. If someone is trying to clean the minerals etc., then it should be as low, it should be high enough so that it can separate into the two phases, and then particles settled at the bottom can be taken and then taken to the next unit operations or unit processes as per the requirement. Okay. So that is the point of calculating this US, so that one can have a kind of estimate time, how much time will it take to separate into the individual phases if it is a suspension, right. So that time has to be large. If it is a kind of separation of the particles, if you are targeting as per your applications, then it should not be very large time, so that it should be settled quickly and then separated out into the two phases as per the requirements, right. So now what we understand here, the correction factor is epsilon square psi p. If you know the single particle free settling velocity, and then if you multiply it by epsilon square psi p, then you will be having a kind of estimate or a priori information about the suspension velocity. Okay. Now similarly, Reynolds number, in the suspension we have this Reynolds number. If you substitute here US, whatever the expression that we got, US is nothing but UT multiplied by epsilon square psi p, and then UM also you substitute accordingly, rho m also you substitute accordingly, then simplify, you will get this expression. Further if you simplify and then rearrange, so you will get, so REPS is equals to REP rho m by rho, this epsilon psi p square, there is no square of this one. So REPS would be REP rho m by rho epsilon psi p square, you will get here. Okay. So that means the correction factor is rho m by rho epsilon psi p square for the Reynolds number. So that is, if you get the Reynolds number of a single particle, that is REP is equals to dp ut rho by mu, you get it. Then if you multiply that one by rho m by rho epsilon psi p square, you will get the Reynolds number of the suspension. So which is going to be much smaller compared to the Reynolds number of the single particle. So this is how the relations we have to develop. Okay. So we see now what are the relations available between these two. Other than these things, is there any other method available or not? So before going to the other methods, what we do, suspension generally do not settle for so fast that there exists any high Reynolds number region. So similar way we can do for the Newton's flow regimes also. So but in general, as I mentioned, Reynolds number is going to be small in general for suspension, less than 0.1 or 1 in general, but there may be cases sometimes Reynolds number may be 4, 5 or maybe up to 10 maximum, something like that. But in general it is not going to be as high as 10 power 3, 10 power 4 or 10 power 5, so that to consider the Newton's flow regime. But however, academically if you try to do similar approach whatever we have done by replacing mu by mu m, delta rho by rho p minus rho m, and then multiplying epsilon right hand side for relative velocity effect, then you get US is equals to UT multiplied by epsilon power 1.5. Earlier we got for Stokes regime, what we got for Stokes regime, you got US is equals to UT multiplied by epsilon square psi p, but in the Newton's regime we get UT multiplied by epsilon power 1.5 only. Similarly, Reynolds number also, here what we got in the kind of Stokes regime, REPS is equals to REP multiplied by rho m by rho epsilon psi p square we got. So, but here REP multiplied by rho m by rho epsilon power 0.5 and psi p multiplied by psi p. This is what we get for the Newton's flow regime. Okay. There are other corrections are also available in terms of the particle Reynolds number. Okay. They are having in this particular form US is equals to UT epsilon power n. So, whatever the previous relation that were developed, we assuming that suspension is a kind of settling only in the Newton's flow regime, and then we have developed the relation between US and then UT, similarly REPS and then REP, so that we can get, like if you have a kind of settling velocity of single particle, you can know the settling velocity of the suspension itself. But sometimes it may also possible that the suspension may be settling slightly at higher velocity, slightly greater than REP1, then or maybe up to REP is equals to 10 or 20, not higher than that one. So, under such conditions obviously Stokes approximation is going to be deviating from the real situations. For that reason, some researchers have developed this kind of expression, that US is equals to UT multiplied by epsilon power n, and then epsilon is the volume fraction of the liquid. So, this n is a function of REP, n is now function of REP, that is what we have to find out here. So, that means in order to know this expression, in order to know, you need to know the single particle settling velocity, and then you need to know n also. There is a kind of additional factor. Epsilon for a given system is anyway known. What is the liquid fraction, one can easily know. Okay. So, what is this n as function of REP, that we have to find out, right. For Stokes regime it is in general 4.6. They are based on the experimental observation by some researchers. Okay. There is no derivation kind of this thing for this. And then for Newton's regime, though it is a very rare, but let us assume sometimes separation of the phases is also required, right. Like mineral washings, as I mentioned. Sometimes you do not want separation of the phases, you want stable suspension, like shampoos or etc., paste etc. So, for them n is going to be 4.6, that is Stokes regime. If the separation of the phases is required, then that is going to be under the Newton's regime in general. So, for that case n is equals to 2.5, right. So, for the intermediate values, they have given n versus REP expression, graphical information is given, right. Let us say if RE is 3, from here what we get? We get n is equals to 4. Right. So, like that if REP is 11, something like this, so then n is going to be 3.5. So, like this way the graphically it is given like this information like this. Okay. So, now we take couple of example problem to use these expressions and then get the required information of settling velocity of the suspension. Example 1, calculate the hinder settling velocity of glass spherical particles having a diameter dp is equals to 1.554 into 10 power minus 4 meter in water at 20 degrees centigrade. This slurry contains 60 weight percent solids. Okay. Solids weight percent is given, but we need epsilon, that is liquid volume fraction. This is weight percent and that also for the solids. So, epsilon we have to find out. The solids density is 2467 kg per meter cube. The density and viscosity of water at 20 degrees centigrade are 998 kg per meter cube and 1.005 into 10 power minus 3 Pascal second, 10 power minus 3 Pascal second here. Okay. So, then we need to calculate the suspension velocity or hindered settling velocity of these particles having constant or same size dp is equals to 1.554 into 10 power minus 4 meters. Solids weight fraction is 60% of the solids in the slurry. Rho p is given, rho water or rho is also given, mu is also given. We need to find out US. What is US? We will do both the approaches. First approach, what we have developed, US is equals to UT into epsilon square psi p. This is assuming that particles are settling in a kind of Stokes regime, right. So, that we do, then graphically we do. For the graphical approach, we have to first find out the REP, then accordingly N we have to find out. So, we see now. So, epsilon is not now, this is 40% liquid divided by the density of the liquid divided by the 40% of liquid and then 60% of solids. If you divide respectively with their densities, you will get volume. So, volume of the liquid divided by the total volume is going to the volume fraction of the liquid 0.622, right. So, 40% is liquid is there, 60% is solids are there. So, 40 by rho and then 60 by rho p, if you do, you get the volumes of liquid and then particles respectively. So, once you know those volumes, so then you can take the volume fractions. So, that is volume of a liquid divided by the total volume, that is volume of particle plus volume of liquid, you will get the volume fraction of liquid phase 0.622. Then rho m we have defined it as epsilon rho plus 1 minus rho p, that is coming out to be 1553 kg per meter cube, right. So, rho epsilon we calculated this one just now, this rho is given and then rho p is also given. So, everything is known. So, if you substitute, you will get this mixture density. Similarly, mixture viscosity you need to find out. So, mixture viscosity mu m is equals to mu by psi p. So, this psi is 1 by 10 power 1.82 1 minus epsilon, epsilon is 0.622. So, psi p is going to be 0.205. So, then US, this we have got UT multiplied by epsilon square psi p according to the first method. So, in this equation we have to substitute all this information. G is known, dp is given, rho p, rho is given, epsilon square you calculated, psi p also you calculated, mu is also given here. So, if you substitute all of these values, you will get US is equals to 1.525 into 10 power minus 3 meter per second, right, such a small value. So, though by numbers it appears like it is a kind of Stokes regime, because dp is also very small, order of 10 power minus 4 meters, and then US is also very small, order of 10 power minus 3 meter per second, and then viscosity is also order of very small, 10 power minus 3. So, by numbers if you do dp ut rho by mu, it seems like it is a kind of Stokes regime. So, it is an acceptable one. So, REPS also you can similarly find out, dp US rho m by mu m epsilon. So, dp US rho m by mu by psi p epsilon as it is. So, then here also now everything is known. So, dp is given, US just you calculated, rho m also you calculated, psi p you calculated as 0.205, epsilon you calculated as 0.622. So, when you substitute all these things, you will get REPS is equals to 0.121, that is a kind of a Stokes regime. Obviously, it will come Stokes regime, because whatever the u that you have calculated, you calculated assuming the Stokes regime. So, whatever the error if at all is there, so that will be incurring here in the Reynolds number also. Okay. So, if the your velocity is whatever the Stokes assumption is, true velocity is also under the Stokes regime. So, then this is also going to be true value. Okay. So, that you can get the true picture of the Reynolds number from the other alternative graphical approach. Okay. So, alternative graphical approach, what we are having, we have to find out the n value, n function of REP. but REP you can calculate only if you know UT. dP you know UT rho by mu. This rho is also known, mu is also known, dP is also known, but UT you do not know. So, since UT you do not know, you cannot calculate RE. So, if you cannot calculate RE, you cannot know US is equals to UT epsilon power, and this equation you cannot use. So, what is the alternative that we have? We have a kind of a previous lecture finding out the K factor or the K expression that we derived, that is dP g rho delta rho by mu square whole power 1 by 3. If you calculate it, and then if it comes out less than 2.6, then it is a Stokes regime. So, then previous equations whatever we have used, they are true ones, and but here n should be 4.25 for a Stokes regime. So, that way we have to do. If it is not under Stokes regime, then we have to do a kind of trial and error kind of thing as we have done previously. So, when you substitute all this value, dP is given, g is known, rho is given, rho p is also given, mu also given, everything is known here actually. In the problem statement, the physical properties, density and viscosity of the fluid as well as the size and density of the particle are given. So, this can be known. When you calculate it, it comes out to be 3.76, slightly greater than 2.6. So, it is obviously not going to settle in a kind of a Stokes regime. If it has to settle in suspension has to settle in the Stokes regime, or the individual particle has to settle in the Stokes regime, the K value should be less than 2.6 or REP should be less than 1. If the single particle is settling in Stokes regime, the suspension obviously will settle in the Stokes regime, because suspension velocity is in general much less compared to the single particle free settling velocity. Why? Because of the hindrance of the neighboring particles, or because of the upward liquid motion, etc. Because of those reasons, the suspension velocity is always going to be very small, or hindered settling velocity of particles is going to be very small compared to the single particle free settling. So, if single particle is not settling in Stokes regime, if single particle is settling in Stokes regime, so then suspension is also going to settle in a Stokes regime. So, but here it is a kind of different one. So, now since K is greater than 2.6, we have to find out the REP before using that REP versus N graph. Okay. So, it is again trial and error approach. What we have to do? You have to assume some value of REP, then calculate the CD value using this correlation. We can also use the CD versus REP graphs as we have done in the previous lecture, but now readily correlation is available. You do not need to refer to the graph. It is indeed this CD value by this correlation and CD value from the graph would be almost close to each other. Okay, this correlation is known as the Schiller-Neumann correlation for the drag coefficient of single spherical particles settling in Newtonian fluids. So, that is experimentally matching very much well with experimental values. So, but now trial and error approach you assume one REP value. From this correlation you calculate CD. So, REP2 if you substitute here, CD is going to be 15.27 something, and then corresponding U velocity you have to find out, corresponding U velocity. So, if you assume RE is equals to 2, CD is going to be 5.27 by substituting REP is equals to 2 here in this correlation. Then that CD value you can use in this UT expression that we derived in the previous lecture, right. So, then you will get calculated UT value as 0.013978. Now, using this UT value, you recalculate REP as dP UT rho by mu. So, you will get this RE calculated is 2.1515, right, and now you have to see the difference is acceptable for you or not. Okay. Though they are looking close to each other, so absolute relative difference is almost 7.5% between these two. So, assumed REP is good enough, but it is not very close to the calculated value of REP is not very close to the assumed value. So, let us make another assumption 2.2. Then when you substitute 2.2 here in this CD correlation, you will get CD 14.077. So, using this CD 14.077 and then substituting here in this UT expression, you calculate UT. So, that is coming out to be 0.01456 meter per second. Then this using this calculated UT by substituting this UT here in this REP is equals to dP UT rho by mu, then you will get recalculated value as 2.24 and then absolute relative difference is 1.866. So, good enough, but further if you try 2.25 similar way you can get the assumed value of you can, if you assume RE 2.25 then calculated RE is coming to be 2.26 in the similar way as other two steps we have done. And then here the absolute relative difference is very much less, 0.56, right. So, now we can say that 2.25 is a kind of a correct Reynolds number. So, we previous approach we assume that REP is less than 1 and then we have used the Stokes regime settling velocity equation and developed the relations, but in reality it is not close to it is close to Stokes regime, but not falling in the Stokes regime. So, there is some error. How much that error is there, that you can get new value of the settling velocity for the suspension or hindered settling velocity here and then compare with the previous approach. So, from this table what we get, REP is equals to 2.25 and then UT is going to be 0.0147 meter per second. So, now REP is known, so you can calculate n value. So, once n value is also known from the graph, so you can find out US because UT, epsilon, n all three are known then. So, from n versus REP plot that just have shown, for REP is equals to 2.25, n is going to be 4.2 something like that. Okay. So, then US is nothing but UT epsilon power n, UT you calculated as 0.0147 corresponding to REP is equals to 2.25 for single particle, epsilon you calculated as 0.622 and then n from the graph you are getting 4.2. So, you can see here 0.002 meter per second is a kind of a suspension settling velocity. It is slightly larger than the previous approach because previous approach we assumed Stokes regime, but in reality using this Reynolds number calculation what we understand that single particle is not settling in the Stokes regime, though it is close to the Stokes regime, but it is beyond the Stokes regime. It is REP is equals to 2.25. So, RE if it is increasing, keeping density, viscosity and size of the particle same. So, this velocity is obviously going to be more. So, that is the reason here we get slightly larger value of the velocity and then seems to be this is more reliable than the previous one, because the previous one is based on the Stokes assumptions, whereas in reality for this problem conditions the particles are not settling under the Stokes condition. It is slightly beyond the Stokes condition. So, the settling velocity is also slightly more than the Stokes velocity conditions. So, that is by other approach we got 0.0015 meter per second. So, if you find out absolute relative difference between two methods, it is approximately 24% with reference to the graphical approach. So, we take another example now. Particles of sphelerite specific gravity 4 are settling under the force of gravity in CCl4. Specific gravity of CCl4 is 1.594 and then particle specific gravity is 4, rather giving the density now specific gravities are given. So, you can anyway find out their densities. The diameter of the particles is 0.1 mm. The volume fraction of spherulite is 0.2. The solid's volume fraction is given, that is 0.2. Okay. So, it is not weight fraction, it is volume fraction is given directly. So, if the solid's weight fraction is 0.2, so liquid volume fraction is going to be 0.8. So, epsilon is given 0.8 indirectly. So, what is the settling velocity of the spherulite, okay, in the suspension, okay, right. So, now we have to follow the similar approach whatever we have done. So, the difference between specific gravities is 4 minus 1.594 is equals to 2.406. Thus, rho p minus rho would be, let us say if I take 999 or 1000 also you can take and then multiply by the specific gravity. So, you will get this rho p minus rho value as 2403.66 kg per meter cube. Similarly, density of CCl4, that is 999.2074 multiplied by 1.594. So, rho is coming out to be 1592.45 kg per meter cube. Similarly, density of the particles also we can find out, and then viscosity of CCl4 is not given, but from the standard data books, reference physical and chemical properties of many of the chemicals are in general available in the standard Paris Chemical Engineering Handbook. We can find it out it as a kind of 1.03 into 10 power minus 3 Pascal second is the viscosity of CCl4 at 20 degrees centigrade. Now, we have to find out first K, right. So, previous example we understand that assuming Stokes regime and then using that US is equals to UT epsilon square psi p expression is giving slight error, right. So, it is better is to find out what is the Reynolds number under which region it is falling under the Stokes regime or beyond the Stokes regime, then proceeding to the solution is going to be better option. So, for that first we have to find out K, because UT you do not know, so REP you cannot know. So, if REP you cannot know, you cannot say that whether it is under the Stokes regime or beyond the Stokes regime. So, that is the reason K we calculate, which is independent of velocity, or there is no velocity term in this K expression. So, that is K is equals to dP g rho delta rho by mu square power 1 by 3. If you substitute all of them and then find out the value, it is coming out to be 3.28. So, it is slightly more than 2.6. What does it mean? 2.6, K value 2.6 is upper limit for the Stokes region. So, anything beyond 2.6 indicate that the particles are not settling in the Stokes region, though it is not too away from 2.6 value, but still it is beyond the Stokes region. So, we have to find out first REP using the approach that we have been finding out as in the previous cases. So, for a spherical particle, UT is equals to square root of 4g delta rho dP by 3 CD rho. This is what we know. So, now here we have to know this CD value in order to calculate this thing. So, for find out the CD value, we need to know REP, which we do not know. So, again trial and error approach we have to follow. So, for CD versus REP relation, we use the same Schiller and Neumann correlation for spherical particles settling in Newtonian fluids, that is CD is equals to 24 by REP multiplied by 1 plus 0.173 RE power 0.657, and then follow exactly the same approach as we did previous lecture as well as the previous problem to find out this Reynolds number by trial and error approach. So, if you do trial and error approach, you can have the results, and then if you do those calculation and tabulate, you will get this information, right. So, if you assume RE is equals to 2, then substitute here RE is equals to 2 here in the CD correlation. So, you will get 15.27 as the CD. This CD value you substitute here in this expression, then you will get UT is equals to 0.011369. So, then once you have this UT value, then you can calculate REP using dP UT rho by mu. So, here now UT you calculated, so RE you can calculate. So, calculated RE is coming out to be 1.805, whereas assumed one is 2. So, the relative absolute difference is around 9.74%. It's a good one, but still you can improve. So, now this RE calculated value is coming smaller than the assumed value. What you have to do? You have to go to the next RE value, which is smaller than the previous RE value, previously assumed RE value. So, now here RE, let us say if you take 1.8 and then substitute here in CD correlation, then you will get CD is equals to 16.72723, this CD value you substitute here in this UT expression, that is square root of 4 by 3 G dP delta rho by CD rho. If you substitute CD there, so then UT you will get 0.010864. So now UT you calculated, so in the Reynolds number expression here you substitute that UT, so then you will get calculated RE value, that is coming to be 1.724919. So it is much improved one. The relative difference, absolute relative difference is 4.17% only, right. Further now you take 1.6, then 1.5, 1.7, like that. If you keep doing so, you will find this when you take RE is equals to 1.68, assumed RE is also coming 1.6739, very close, with a relative absolute difference less than 0.5%. So what we can say now, the REP is 1.68, and then corresponding UT, whatever corresponding U is there, that is the UT 0.0105 meter per second, and then epsilon is given anyway 0.8, that is solids volume fraction is given. So 1 minus the solids volume fraction is the liquid volume fraction 0.8. So from REP versus N graph, if you see for REP 1.68, N should be close to 4.3, something like that. Then US is equals to UT multiplied by epsilon power N. When you do this, you will get suspension velocity 0.00402 meter per second. The hindered settling of the particles is 0.00402 meter per second, whereas the free settling of single particle is 0.0105 meter per second, right. Almost 50 times it is less than this value. Okay, so you can say that suspension velocity is in general, as we said, very much smaller compared to the single particle free settling velocity. Or hindered settling velocity is going to be much smaller compared to the free settling velocity of the same size particles in a same fluid. So this is how we have to calculate problems associated with the hindered settling. References for this lecture. The most of the lecture is prepared from this book, Unit Operations of Chemical Engineering by McCabe, Smith and Harriet. Ortego-Rivas, Unit Operations of Particulate Solids, Theory and Practice is the another good reference book. Colson and Richardson's Chemical Engineering Series, 2nd volume by Richardson and Harker is also a good reference book. But the problems discussed here in this lecture are taken from this reference book, Transport Processes and Unit Operations by C.J. John Coplis, Unit Operations by Brown et al., and Introduction to Chemical Engineering by Badger and Banchero, also good reference books for this motion of particles through fluids, especially single and hindered settling. Thank you.